The question here is, what is Newton's law of gravity? Here is the description of Newton's law of gravity, or sometimes referred to as Newton's law of gravitational attraction. So in addition to the three laws called Newton's laws that we looked at in another video, Newton also postulated a law governing the gravitational attraction between two particles as follows. Supposing, say, there are two particles, 1 and 2, with mass m1 and m2 respectively, and separated by a distance r, like shown in this picture. Newton then postulated there's an attractive force between the two particles 1 and 2 called the gravitational attraction. He said that the magnitude of this attraction is quantitatively given by this equation right here. F equals g times m1 m2 divided by r squared. G here is what is called the universal constant of gravitation, and it has a value given by this 66.73 times 10 to the minus 12 meter cubed over kilogram times second squared. So these are the units of this universal constant of gravitation. Don't worry too much about the units here because we're going to be discussing units in detail in the next video. So this equation gives the magnitude of F, and what is the direction of F, right? Well, the direction of F is on a straight line connecting the two centroid of particle 1 and centroid of particle 2. Once again, if you remember the definition of centroids from physics, that's good. Otherwise, don't worry about it. We're going to come back and talk about those in detail again later on. This equation here is a very general equation. You can apply this between two particles, any two particles. The particle could be a particle and Earth, Earth and Moon, two stars, and so on, right? Well, let's see if we can extract the value for Earth's gravity from this equation. Alright, I brought Newton's law of gravity from the earlier slide, and here's the value of G. Our objective here is to see if we can find a value of Earth's gravity, little g. Here's a little schematic showing what we are trying to do here. Here is the Earth, and here's a little object sitting on Earth. Say the mass of Earth is capital M, and the mass of the object is little m. RE here is the radius of the Earth. R is the distance between the Earth and the object. W here is what we normally refer to as the weight of the object. We know the weight comes from the gravitational attraction between the Earth and the object, and therefore F equals W. And F by this equation is G multiplied by capital M times small m divided by r squared. And we also know weight W equals mg, mass times the gravitational acceleration. Here, the object that I have in mind is the usual small object, like the iPad that I'm writing on right now. In that case, you can see that the radius of the object is so small compared to the radius of the Earth that the sum of the two, that is RE plus the radius of the object, will be approximately equal to R. And in that case, after cancelling this little m from both sides of this equation right here, G becomes equal to capital G multiplied by capital M divided by RE squared. We have values for each of the three parameters in this equation, right? So let me list them, substitute them in this equation and see what we get for little g. So here's what I have. Mass of Earth is 5.972 times 10 to the 24 kilogram. The radius of Earth is 6.371 times 10 to the 6 meters. We already have a value for capital G, so we substitute everything in this equation, right, in this equation. And we get a value of 9.81 meter per second squared for little g, the gravitational acceleration. You might have learned in physics that this is the correct value of little g, right? Also, in US customary unit system, which is another unit system that we commonly use, G is 32.2 feet per second squared.